The purpose of these lectures on acid-base chemistry is to help you differentiate between the strength of two or more different acids. In the previous lecture, I talked about different tools that we use in order to compare acid strengths. The first tool is to memorize a list of strong acids. That list of strong acids does not include all the known strong acids in the world, but it includes the strong acids that we commonly encounter in the context of organic chemistry. That list is right here. This is from the notes when I teach general chemistry, and the list is pretty consistent. These are the strong acids that we will commonly encounter in the context of organic chemistry. And if you know this list, then when you're asked to compare the acid strength of two different acids, then if one of them is on the strong acid list, like hydrochloric acid, and the other is not, then it's a safe assumption that this is a stronger acid. That comparison, that tool of knowing your strong acid, works from time to time. Today we want to continue to talk about additional tools that allow us to compare acids that are not necessarily strong acids. And the second tool I introduced in the previous lecture, and this was knowing a handful of pKa values. The pKa values that you need to be familiar with, that kind of store in the back of your mind and be ready to pull them out whenever you need them, are the alcohol pKa of about 16, amines of about 36, protonated alcohols with a value of approximately -2, aminium ions or protonated amines with a value of about 9, and finally carboxylic acids with a value of about 5. Knowing these 5 pKa values is probably going to be the tool that you use most commonly when you're comparing acid strength. That allows us to look at question number 2 and question number 4. Yes. Question number 2 has ammonia, which is kind of the simplest possible amine, and I'm comparing it to water, which is the simplest possible alcohol. Ammonia has a pKa of about 38, so it's in the ballpark of the 36 that you need to memorize, and water has a pKa of 15.7 in most solutions, which is close to that memorized value of 16. Something with a pKa of 16 is a stronger acid than something with a pKa of 36. Now in number 4, we can compare the nitrogen with a positive charge and the nitrogen with a neutral charge. Nitrogens with positive charges have a pKa of about 9. Nitrogens with neutral charges have a pKa of about 36. 9 is a lower value, stronger acid. So this knowing of these 5 pKa values allows us to compare a lot more acids than just knowing the strong acid table. Here is another summary of Tool 2 that I've given you, where alcohols have a pKa in the ballpark of 16. Here I'm reporting it more as a range. It still gives you approximately the same idea. Alcohols are 16 to 18. Oxygens with a positive charge are about -2. Amines are about 36. Nitrogens with positive charges are 9 to 10. And carboxylic acids are 3 to 5. So this is Tool 2, a short list of memorized pKa values. You should be able to use this list to place the 3 indicated hydrogens in order of increasing acidity. So go ahead and pause the video and decide which of these 3 hydrogens is the most acidic and which of these 3 indicated hydrogens is the least acidic, and then restart the video and we'll see how you did. This is a carboxylic acid. This carbon right here is doubly bound to an oxygen, which makes a carbonyl group. The carbonyl group, when positioned next to an OH group, is what collectively makes this a carboxylic acid. Its pKa is going to be in the ballpark of 3 to 5, usually closer to 5. This is a nitrogen with a neutral charge, or an amine, and it has a pKa of about 36. And this down here is just an alcohol, an OH group with a neutral charge with a pKa of 16. The carboxylic acid's pKa of 5 makes it the strongest acid. The amine with a pKa of about 36 makes it the weakest acid, and the alcohol is in the middle. So strongest acid here, second strongest on the alcohol, and weakest or third strongest on the amine. If there isn't a strong acid, which means we can't use tool number 1, the list of known strong acids, and you don't know the pKa values, which is tool 2, then tool 3 is a comparison of the acids based on their structure. The most important thing that you have to do when you're comparing 2 acids based on their structure is you have to identify which atom is bonded specifically to the acidic hydrogen. Once we've identified the atom that's bonded to the specific acidic hydrogen in each of your two acids, then we're going to break it down into categories. So let's go back and see how this applies to the practice problem right here. Let's talk about this compound. This is CH3OH versus CH3SH. We want to know which of these two is the most acidic. The hydrogen connected to the oxygen is the acidic hydrogen of methanol, and the hydrogen connected to the sulfur is the acidic hydrogen on this compound on the right. We know that the pKa of an alcohol is going to be in the ballpark of 16. We don't necessarily know the pKa of this hydrogen bound to the sulfur. So our first thing that we do is we identify that the hydrogen in this case is bound to an oxygen, and here the hydrogen is bound to a sulfur. Oxygen and sulfur are different atoms. So if we go back to this list, what I've done, so we determine which atom is bound to each acidic hydrogen. One of our acids has the hydrogen bound to an oxygen. The other acid, the hydrogen is bound to the sulfur. Now we're going to use that knowledge to find a category. Category 1 tells me that the atoms are different, and that's true. The two atoms I'm comparing are the oxygen and the hydrogen. In category 1, the atoms are different, but they're in the same row of the periodic table. Oxygen and sulfur are not in the same row of the periodic table. Oxygen's in the second row, sulfur is in the third row. So this category does not apply. Category number 2 is where the atoms are different. That's true, and they are in the same column of the periodic table. Let's pull up our periodic table so that we can verify that this is the case. Oxygen here, sulfur here, they are in the same column of the periodic table. Category 1 looks at things that are in the same row. Category 2 looks at things that are in the same column. What happens if they're not in the same row or the same column? Well, in that case, we really hope that one of them is a strong acid, or we know the pKa values. This structure analysis that I'm showing you does not allow you to compare every possible pair of acids. It's just trying to cover most of the ones that you're going to see in the context of this course. So for category 1 to work, the atoms have to be different and they have to be in the same row of the periodic table. For example, category 1 would allow us to compare NH3 and CH4. Category 2 is where the atoms are different, but they're in the same column of the periodic table. And that's the example we're looking at right now, but it would also work for hydrofluoric acid and hydrochloric acid. Let's go back to those categories. Right here. Okay. So category 3 and category 4 are when they're the same atom, and that doesn't apply yet, so we won't think too hard about that. So let's go ahead and look at this in the context of the practice problem. Here is the example we're looking at, CH3OH and CH3SH. We're comparing the hydrogen connected to the oxygen and the hydrogen connected to the sulfur. This is a category 2 where the atoms are different, but they're in the same column of the periodic table. When that's the case, the larger atom is the stronger acid. And I know that I've left some words out here that I'm adding in. It's because of the space of what I was allowed to type in the box. So when we move down the periodic table, which we're doing, going from oxygen to sulfur, the acids become progressively stronger. So of these two, this compound on the right is the stronger acid because the sulfur is further down the periodic table than the oxygen. Now let's look at number 2, NH3 versus H2O. Now we don't necessarily need to use these categories because we know pKa values for those, but let's assume that you forgot your pKa values and you have to rationalize this based on tool 3, which is structure. In this compound right here, the acidic hydrogen is connected to a nitrogen. In water, the acidic hydrogen is connected to an oxygen. So the acidic hydrogen in question number 2 is connected to different atoms. Those atoms are nitrogen and oxygen. Nitrogen and oxygen are in the same row of the periodic table, and therefore we use the rule that the more electronegative atom makes for a stronger acid. Or in other words, because oxygen is more electronegative than nitrogen, and they are in the same row, then water is a stronger acid than ammonia. Notice that the electronegativity rule only applies when they are in the same row. When they are in the same column, but different rows, then electronegativity would give you the wrong answer. Oxygen is more electronegative than sulfur, But this compound is a weaker acid. And that's because when you are moving down columns, then the larger atom becomes more acidic, and that is independent of electronegativity. Now, the reason for that is not something I'm going to talk about. All right, now let's look at question number 4. Here, the acidic hydrogen in both cases is connected to a nitrogen. So here, in question number 4, it is the same atom. So we're looking at either category 3 or category 4. Category 3 says that the acidic hydrogen is connected to the same atom, but the charge is different. So in this case, the charge, the nitrogen on the ammonium, has a positive charge, and in ammonia it has a neutral charge. The more positive charge, it makes for the stronger acid. So based on category number 3, we would state that the ammonium, the NH4+, is a stronger acid than ammonia. If you know your pKa values, then we wouldn't have had to do this analysis. You could have used the pKa values to tell you the same information. But if you forgot your pKa values, then category 3 rule allows us to state that ammonium is a stronger acid than ammonia. Finally, let's look at number 5. These are both carboxylic acids. We have a carboxylic acid here and a carboxylic acid here. The acidic hydrogen in both cases is not part of a strong acid, so we can't use the first tool of knowing our list of strong acids. And all carboxylic acids we've memorized a similar pKa value of about 5. So tool 2, even though I know the value, isn't going to help me here because both of them are part of the same family. They're both carboxylic acids. So I'm going to have to evaluate it based on these criteria. The hydrogen that is acidic is this one out here. And in both compounds, that hydrogen is connected to an oxygen. So the hydrogen is connected to the same atom. The charge is also the same. Both of these are neutrally charged compounds. You notice that I don't have a little positive charge written anywhere down here. So that means that I'm looking at category 4, that the acidic hydrogen is connected to the same atom, but the neighbors on that atom are different. So this carboxylic acid is neighbored by a methyl group, and this carboxylic acid is neighbored by, we call this a trichloromethyl group. So in the case of example number 5, when the only thing that's different are these neighbors, then the more electronegative neighbors make for a stronger acid. And this has nothing to do with where they are in the periodic table, because we're attached the hydrogen to the exact same atom. So moving up or down the periodic table doesn't matter when the hydrogen is connected to the same atom. The location up or down on the periodic table only matters when the hydrogen is connected to different atoms. That's rule number 2. In this case, chlorine is more electronegative. We're using rule number 4, and therefore this compound is going to be a stronger acid. And it's actually quite a bit stronger. I think the pKa drops by 3 or 4 units, which is actually 3 or 4 orders of magnitude. So the correct answer is now in questions, we should have all these. Question number 1, hydrochloric acid is a strong acid, so it's the stronger one. Question number 2, pKa of water is about 16, ammonia is about 36, so this is a stronger acid. Question number 3, this is the stronger acid because sulfur is further down the periodic table based on rule number 2. Question number 4, we can either use the pKa values or we can use rule number 3. The more positive charge on the same atom makes for a stronger acid. And in question number 5, the hydrogen is connected to the same atom, but the more electronegative neighbors make for this a stronger acid. Let's look at another example of this. So I would encourage you to pause the video and predict the direction of equilibrium. Okay, hopefully you're back. In the case on the left, this is an alcohol, and the alcohol is losing its hydrogen as we move from left to right, so that makes this the acid. Therefore, this is my base, this is my conjugate base, and this is my conjugate acid. So the thing that loses its hydrogen is the acid, and whatever's left of it is the conjugate base. And that should allow you to figure out what the base and the conjugate acid have to be by process of elimination. This alcohol right here has a pKa in the ballpark of 16, and this is a carboxylic acid with a pKa in the ballpark of 3 to 5. So, based on tool 2, where we know the pKa values, we would expect for this to be the stronger acid, and equilibrium favors the formation of the weaker acid. This equilibrium would shift us back towards our reactants. In this one down here, we actually have a lot more information than we need because we're mixing hydrochloric acid with a compound that we're not very familiar with. We've not talked about the pKa of this compound. And it's going to produce hydrochloric acid. It's my acid. There's my conjugate base. Therefore, this is my conjugate acid. I'm comparing hydrochloric acid with this. This is acetone right here. And hydrochloric acid is a strong acid. That's tool number 1. That's the list of strong acids that we memorize. So we predict that equilibrium shifts over to the right. The reason that I have this little red KEQ is about equal to 10 to the difference in pKa is that this is a useful rule of thumb. And the math on this is pretty straightforward. What you do is you look at your pKa values. Here we have a pKa of 19 and we have a pKa of negative 3.9. For the sake of doing quick math, I'm just going to call this a pKa of negative 4. In fact, why don't I just change the slide? They don't have to tell people I'm assuming this. Okay? Forever hereafter, this pKa will be a negative 4. The difference between those two pKa values is 23. Okay? So 19 minus a negative 4 gives me a positive 23. That tells me that my equilibrium constant for this reaction is 10 raised to the power of that difference. We always take the final minus the initial. So it is 19 minus negative 4 tells me that the equilibrium constant for this reaction is 10 to the 23rd. That's a very large equilibrium constant. If it's anything greater than 1, then we expect it to favor the products. If it's 10 to the 23rd, that means that for every 10 to the 23rd molecules that are on the product side, we have about 1 of them that are on the reactant side. 10 to the 23rd, you might remember that's the exponent of a mole. So for every mole of compound, you have 1 of them will stay unreacted. And at that point, your equilibrium arrow really should just be a one-directional arrow. This is not really in any meaningful equilibrium. Let's look at another example dealing with tool 3. So I want to talk about the acid strength of all 4 of these compounds. And all 4 of them are alcohols. Alcohols are not on the table of strong acids, and so the tool number 1, knowing our strong acids, is not helpful in terms of us being able to differentiate which of these is the strongest and which of these is the weakest. I have given you the pKa values off to the side, so that tells you that methanol is going to be stronger than ethanol, which is stronger than isopropanol, is stronger than terbutanol. Those are names that you don't necessarily know how to say or how to come up with yet. I imagine you can say them. All right, so just for a second, ignore the pKa values. If I hadn't given you these numbers, you would just recognize that all of them are alcohols, hopefully, and they all have a pKa in the ballpark of 16. And so what you would not be able to do without the pKa values is tell me which is the strongest and which is the weakest unless we use tool 3. In all cases, the acidic hydrogen, the red one, is connected to the same atom. When the acidic hydrogen is connected to the same atom, let's go back. If it's the same atom and the charge is different, then we can go based on the charge. But the charge is not different. Every one of these has a net neutral charge. There's no positive or negative charges anywhere. So now, if we have the same atom and the neighbors are different, then we have to go with more electronegative. And the problem here is that all of these are just surrounded by carbons and hydrogens. So this introduces an important concept that is, let's go ahead and draw this in. There are electron donating groups, EDG, and there are electron withdrawing groups. They're opposite of each other. Electron withdrawing groups pull electron density away from the acidic hydrogen. So if this methyl group were an electron withdrawing group, then the electron density would move away from the hydrogen. If you take electrons away from this bond right here, then you make that hydrogen more acidic and you give it a lower pKa. But this methyl group is not an electron withdrawing group. Carbon and hydrogen have a lot of electron density and they don't hold it very tightly. So they are generally regarded as electron donating groups. And electron donating groups actually push electron density in towards the oxygen. And in doing so, they actually add to the amount of electron density that glues the oxygen and the hydrogen together. When you have an electron donating group like this, it pushes electron density in towards that bond, and it makes it a weaker acid. And 15.2 is not a strong acid, so that's why. The electron donating capability of the methyl group is what gives us the pKa of 15.2. If you continue to add more carbons and more hydrogens, which is what we're doing here, we've got more carbons and more hydrogens, as you go down the list, the amount of donation that occurs, the ability of that hydrocarbon right here to donate electron density keeps increasing. So it's more and more and more electron density is being shoved towards the oxygen as you move down this list. And if you put more electron density right here in this bond, then that more effectively glues that hydrogen in place and your pKa value is going up. This is referred to as the inductive effect. The inductive effect tells us that the neighbors attached to the other side of the acid hydrogen can either push, if they're electron donating groups, or pull, if they're electron withdrawing groups, electron density to or from that acidic hydrogen. If they push, then it makes the hydrogen stick harder, stronger, and it's a weaker acid. If they pull, it will cause the electron density to leave that hydrogen and it becomes a stronger acid. Let's see. There's got to be an easier way to do this. I don't want these notes. All right. So let's go ahead and see if we can apply what we've learned. We want to talk about direction of equilibrium in the reaction of hydroxide and bicarbonate. So what I would like you to do is pause the video and draw out the mechanism for the reaction of hydroxide with bicarbonate. That's HCO3-, predict the products, and come up with the direction of equilibrium. You don't have to do this part right now. So go ahead and pause the video and see if you can do that. Okay, so I drew out a mechanism for this reaction. The hydroxide is the base, rips a hydrogen off of the bicarbonate to produce water as a conjugate acid and carbonate as a conjugate base. One of the things I want to illustrate with this question is you can actually compare bases. So in the past, we've always done our comparison of equilibrium to decide which direction is favored at equilibrium by identifying the acid and the conjugate acid and comparing those. And you can definitely do that here if you like, but in this particular case, I want to talk about the bases. So equilibrium favors the formation of the weaker acid, but it also favors the formation of the weaker base. And the way that conjugate acid-base strength interacts is that you'll always end up with the weak acid and weak base on the same side. So in other words, if you identify the weak base, then that equilibrium, knowing that the equilibrium will go that direction, still works. So let's talk about these two bases right here. In terms of bases, right, base strength is a function usually of charge delocalization or charge concentration. So what that means is a stronger base. Remember, the job of a base is to take its negative charge and go grab something. And so the more that negative charge is localized to a single point, the better the compound is able to go out and reach out with that charge. So in the case of hydroxide, that -1 charge on the oxygen has nowhere else to go, and it is stuck on this oxygen. So this oxygen right here has a concentrated -1 charge. In carbonate, there are 2 negative charges, but because of resonance, those 2 negative charges are actually distributed across all 3 oxygens. You can actually imagine a resonance structure, and I'll show an arrow. If this lone pair were to drop down to form a double bond here, and that double bond were to break out onto the oxygen, then we end up with a resonance structure for carbonate that looks like this. I'll grab these, and I'm just going to take it and turn it. If I turn it like this, then it's true, just like that. So what I just did is showed you that if I take that lone pair and drop down, I can make a double bond, and that takes the old double bond and pushes it out onto that oxygen on top. And the point that I'm getting to is that this carbonate actually doesn't have a -1 charge on the oxygens. Because of resonance delocalization, those 2 negative charges are evenly distributed across all 3 oxygens and therefore the true charge on the oxygen in carbonate is a negative 2/3. And bases are stronger when the charge is higher on each individual atom and more concentrated. So hydroxide is a stronger base than carbonate because the negative charge on the oxygen is more concentrated onto the oxygen in hydroxide than it is on carbonate. That means that hydroxide is the stronger base and carbonate is the weaker base, and equilibrium will favor the formation of the weaker base. So equilibrium favors the products in this reaction. The second part of this question asks about Lewis acid electrophiles and Lewis-based nucleophiles. This is a fairly simple complex that's unfortunately packaged in a lot of big words. So let's go back and look at the chemistry that we did right here. The hydroxide base reaches out its electrons to go grab a hydrogen off of the bicarbonate acid. In general chemistry, we would refer to this as a Bronsted-Lowry acid, where the bicarbonate is giving up its hydrogen. But I've been describing it, hopefully consistently, as we want to think about things from the perspective of the electrons. And so Lewis came up with a different definition for acids. So the Bronsted-Lowry acid definition is down here. Bl stands for Bronsted-Lowry. And the definition that Bronsted-Lowry has is a proton donor. Lewis acids are opposites in both ways. So the opposite of a proton is an electron. Electrons always come in pairs, so even though it's not exactly the opposite, we're going to say that the opposite of a proton is an electron pair, and the opposite of a donor is an acceptor. So all Lewis did was give us a definition for an acid that was based on thinking about the movement of electrons. Something that is a proton donor, such as bicarbonate, is donating that proton because, from the perspective of organic chemistry, it's accepting a pair of electrons from a different ion or molecule. And a Bronsted-Lowry base, which was hydroxide, is a proton acceptor. That was the definition we used in general chemistry. In organic chemistry, we're going to define our Lewis base as opposite in both ways. So instead of a proton, it's now an electron pair. Instead of an acceptor, it's now a donor. Lewis base is an electron pair donor. So these definitions of Lewis acids and Lewis bases are the definitions that we're going to talk about most of the time when we deal with acid-base chemistry. So you've graduated. You've moved past the idea of acid-base chemistry being about protons. Now acid-base chemistry is about electrons. For reasons I don't really know, and maybe it was an attempt to make things easier, instead of calling things Lewis acids, we decided to give it another word. And these terms are synonymous. So a Lewis acid is also called an electrophile, and a Lewis base is called a nucleophile. Electrophile means loving electrons. So this hydrogen right there is loving the electrons that it's getting. So that makes it a Lewis acid electrophile. And a nucleophile is something that loves a nucleus. This oxygen is pushing its electrons into the nucleus of the hydrogen, evidently because it has strong romantic feelings for it. So that's the term nucleophile. Another example of Lewis acid-base chemistry, we can look at just the autodissociation of water, or autoionization of water, that generates some small amount of hydronium and hydroxide in any pure water solution. One of the water molecules is going to push its electron pair, so that is an electron pair donor. A Lewis base is an electron pair donor. So by the Lewis definition, this water is a base. By the Lewis definition, this hydrogen right here is the acidic hydrogen of the water because it is accepting a pair of electrons. Again, emphasizing that Lewis acid and base definitions are focusing on the electron movement that we love to talk about as organic chemists. The reason that this Lewis definition is better is because it allows us to talk about acid-base chemistry that does not involve the movement of hydrogens. So this reaction right here involves ammonia reacting with boron trichloride to form this conjugate product right here. I don't even know the name of it. And this is an acid-base reaction, but it's not a Bronsted-Lowry acid-base definition or reaction, because in Bronsted-Lowry acid-base reactions, you have to move hydrogens around. And here, the hydrogens always stay connected to the nitrogen the whole time. And so this is not a movement of protons, not Bronsted-Lowry. But it is Lewis. So this is an acid-base reaction because the definition of a Lewis base is an electron pair donor. The nitrogen is donating its pair of electrons to the boron. That makes it a base. The boron is accepting a pair of electrons, which makes it an acid. Those synonymous terms tell us that things that are Lewis bases are called nucleophiles. So this is my nucleophile, this is my electrophile, and this is the product of the nucleophilic addition of the ammonia to the boron trichloride. We are going to talk about Lewis acids and bases most of the semester, but we're going to call them nucleophiles and electrophiles. And what I'm trying to show you is it's just a different way of thinking about acid-base chemistry. As a final note, just to make sure that you understand the relationship between Bronsted-Lowry acid and bases and Lewis acid and bases, anything that is, so the Bronsted-Lowry acid base is kind of a very specific and narrow definition. And it worked great in general chemistry, and it's actually worked pretty well most of the time in organic chemistry, but it has some limitations. So if you think about everything in the world that's an acid or a base, the Bronsted-Lowry incorporates an amount of that. It draws some boundaries and says it's about acid, it's about moving hydrogens or protons around. The Lewis acid base is a broader definition that incorporates everything that is a Bronsted-Lowry base or acid and then adds to it. So the Lewis definition encompasses everything that Bronsted-Lowry communicated, but then gives us more things that are acids and bases. And we're going to do a bunch of organic chemistry out here that we can think about as acid-base chemistry that's not the Bronsted-Lowry acid-base chemistry that you learned in general chemistry. Perhaps to help you differentiate between what you saw in general chemistry and what we're going to talk about in organic chemistry, we stop referring to Lewis acid-base chemistry as necessarily Lewis acid-base chemistry and just refer to it as the reaction of a nucleophile with an electrophile. But this is just kind of a fancy way of trying to avoid saying the word acid and base because we're so used to thinking about it in this context that sometimes we get confused when we talk about it in this context. So we're going to use the term nucleophile and electrophile to talk about this world out here for the rest of the semester.